A theme of the previous video was that there is a maximum distance in which you could look out into the universe. The reason for that is there are objects in the universe that have given off light. This light travels at the maximum possible speed. It has been traveling at the maximum possible time, the entire age of the universe, and that light has barely had enough time to reach our telescopes. And presumably there is a even more distant object that has been giving off light, but this object just hasn't had enough time for its light to reach us. So we are sure there are things out there, but we just can't see them because their light has not had enough time since the beginning of the universe to reach us. We could also think about looking out into the universe as seeing objects as they were in the past. This is basically what we talked about in the previous video in terms of look back time. So a natural question to ask is, can we look back all the way to the Big Bang? So if we look out really far into the universe, can we see the beginning of the universe itself? Well, the answer to that question is not if we're looking with light. And this is going to be due to the fact that the universe is expanding. So the universe, the distance between every location in the universe is growing with time. Now, when you take a gas of particles, if you compress the gas temperature increases. And if you have gas in a chamber, if you increase the size of the chamber without letting any gas in or out, the temperature of the gas inside that chamber is going to decrease. So as we move back in time, the universe used to be smaller, the distance between every location was smaller, and the universe was growing hotter and denser. And if we allow this trend to continue to its extremes, there comes a certain limit where the universe will become opaque. So right now, empty space with a few atoms here and there are transparent, light could travel through it. But the universe used to be opaque, where light could not travel through the universe. Above a certain temperature, neutral hydrogen can't exist, so hydrogen will lose its electron. Hydrogen is the simplest element. It consists of one proton and one electron. At these very high temperatures and pressures, when the universe was really, really young, a proton might capture an electron for a moment. So for a very brief moment, you will create a neutral hydrogen atom. But nearly as soon as the proton captures the electron to form neutral hydrogen, that neutral atom is going to collide with some other particle and that electron will be kicked away again. So you don't have stable neutral hydrogen. So the early universe was very dense, very hot, filled with a hot plasma, and neutral hydrogen could not exist. So one consequence of this is that the early universe was really dense, really hot, and with neutral hydrogen not being able to exist, the universe was also opaque. But as the universe expanded, you had a gas in an expanding container, that container being the universe. The temperature of that gas cooled. And when the universe cooled below a certain temperature, protons that could capture an electron were actually able to hold on to that electron and could keep it now. And when this occurred, the universe went from a really hot, dense, opaque substance to being filled with a cooler, dilute, and now transparent substance. So when this occurred, light was actually able to travel through the universe. An analogy of this could be thought of as a foggy day. So in the very early universe, light would travel a really short distance, but then it would collide with a particle, travel again, bounce off that particle, scatter again. It would scatter all over, bouncing off many particles. But the universe at some point became transparent to light as the temperature of the universe cooled, and light could then free stream and travel across the length of the universe. Now, if we look out into the universe, we are looking back into time. So we look, 1 million light years ago, in 1 million light years away, we're looking at the universe from 1 million years ago. The universe was ever so modestly hotter, but it was still transparent. And then 1 billion light years ago, the universe was a little bit hotter, but it was still transparent to light. But if we go back more and more, we eventually cross the distance upon which the universe becomes opaque to light. So if I imagine myself standing here and looking out in every direction, when I look out, I'm looking backwards in time. There will be the surface surrounding me that is the moment when the universe went from opaque at really early times to transparent at more recent times. And this is known as the surface of last scattering. An analogy for the surface of last scattering could be thinking about looking up on a cloudy day. So if the sun is out on a cloudy day, you don't see the sun, but everything is still lit up. You have the sun way high above the clouds, the sunlight hits the clouds, and that light is going to bounce off lots of atoms in the clouds. But as the light eventually hits the base of the clouds near the bottom, that light will scatter off the last atom near the bottom of the clouds, and then that light could just travel down towards the surface where you are looking up at the clouds. So from the base of the clouds to your eyes, the air is transparent. But above the clouds, where the light is bouncing all over, the air is opaque because it's very cloudy. This is kind of similar to what the universe did. You had an opaque, almost you could think of it as cloudy surface. But then when the universe got cooler and expanded in more recent times, the universe became transparent and light could travel through it. And we see this light coming from every direction. When we look out into the universe, we are looking back in time. So at really early times, which could also be phrased as looking in really distant parts of the universe used to be opaque, but at some moment the universe became transparent to light, and light could actually travel through the universe and reach Earth, where we are today. So what we see is a very uniform haze of light known as the cosmic microwave background radiation, or CMB. Now the universe, the CMB, is almost a perfect black body. The CMB is the most perfect black body ever measured in science. So if we were to look out and make a temperature map of just the universe, we're only looking out into the universe, looking at the sky. Let's pretend we remove the galaxy, we remove stars in the universe. We just look at empty space. We would see just this uniform glow of light that is a nearly perfect black body. We talked about black body radiation and its connection to temperature in some of the background slides on science topics. And today, this background temperature corresponds to a temperature of about 2.7 Kelvin, or 2.7 degrees above absolute zero if you were measuring in Celsius. So this black body radiation comes towards us from every direction on the sky uniformly. The spectrum of light corresponds to a very uniform temperature, but okay, we're looking at a resolution temperature map from absolute zero to 6 Kelvin. 6 Kelvin is basically 6 Celsius above absolute zero. Kelvin and Celsius are the same thing, only 0 Celsius is where water freezes, 0 Kelvin is absolute zero. Let's imagine we improve the resolution of the temperature map. So if I want to improve the resolution of this temperature map, I might realize that our galaxy is actually moving through the universe. Our galaxy moves at 390 kilometers a second, which is, I don't know, I'm going off the top of my head, let's say 225 miles a second. So our galaxy is moving through the universe. Now, if we were to move through the universe, one side we're looking at light in the direction we're moving towards will be blue shifted. Light in the direction we're moving away from will be red shifted. We talked about this in the background science slides. So if we are moving to the right in this picture, light is coming from us uniformly in every direction, but the light in the direction we're moving towards will look a little bit bluer. The light in the direction we're moving away from will look a little bit redder. And this is known as the CMB dipole. So this dipole does exist, it has been measured, and this is just due to the fact that our galaxy is actually moving through the universe. So we have a temperature of about 2.7 Kelvin above absolute zero, and this distortion of this temperature map, the light that we're observing, is going to be only a factor of about 0.1%, or 1 part in 1,000 change in the color of the light that we see. Now, let's remove the foreground sources in such as the stars and galaxies again, just like before. Let's also remove the dipole. The dipole is just due to the fact that our galaxy is moving through the universe. Let's ignore that. We really want to know about the universe. And if we take a temperature map of the sky and we look at the CMB in really good resolution, we get a map that looks something like this. And you could tell from how slowly the map has risen that it is important. So, wow. In this map, this is a temperature map of the sky, just like the map we made right here, but instead of going from 0 to 6 Kelvin, the red spots in this temperature map are about 0.00001 Kelvin hotter than the cold blue spots. So this is a very detailed map, temperature map of the sky where we removed our galaxy, we removed nearby stars. We're looking at the primordial universe in this picture. Now the hot red spots in this map are primordial density fluctuations. So these are regions of the early universe that were slightly denser than average. These slightly denser than average regions in the universe are going to eventually collapse under gravity and form galaxy clusters. The cold spots in this map, which are slightly colder, only by 1 part in 100,000 compared to the hot spots, these are slightly emptier regions in the universe, and these will eventually form cosmic voids where there is very little material. Now remember that this map of the universe that we're looking at is a really early snapshot of the universe. We're looking at the universe just 300,000 years after the Big Bang. So proper galaxies, proper voids don't really exist yet. Now, this CMB is only one picture of the universe. So the previous slide was a temperature map of the sky, and more properly, we could say it's a temperature perturbation map. We're only looking at slight variations in the temperature on the sky. The CMB actually approaches us from every direction, with us imagining that we sit at the center of the universe. Kind of like in this picture here from a previous video, where we imagine that we are sitting here and we have light approaching us from every direction in the universe. There might be other locations or vantage points you could look at where light would be approaching from everywhere else, but we don't have the ability to go elsewhere in the universe and look at the universe. We have only one vantage point to look at the universe from. So the CMB is a phenomenally rich source of information on what makes up the universe. It is possible to simulate what would the CMB look like for a universe if the universe had more dark energy, or what if the universe had a different value for the Hubble constant, or what if our universe was colliding with another universe? What would the CMB look like in those scenarios? And it's possible to simulate what you would expect the CMB to look like. And changing these properties affects the size and the distribution of the hot and the cold spots. And sometimes these changing these factors even puts patterns onto the CMB that it is possible to look for. So the CMB is another really strong piece of evidence for the existence of dark matter, dark energy, where we could predict how much matter is in the universe. We could predict how much dark energy is in the universe based on properties of the CMB spots that people could look for. Now, for the most part, we only have one sky that we can actually look at. So it's not possible to travel far away from Earth and look at the sky from a different vantage point. In cosmology, this problem is known as the measure problem. We only have one sky that we can look at, and that's all we get. For example, this dark spot right here is believed to be due to a really large void that lies between us and the CMB. But this void, based on how we understand structure formation, is a lot bigger than we think voids should exist. Our current models of structure formation predict that it's unlikely that you would just coincidentally exist in a universe, exist in a certain region where a void this large would exist within your observable universe. But the problem with that is the odds of us having a void this size inside our universe are about 1%. So maybe this cold spot is evidence of unknown physics or something we don't know about structure formation. Or maybe we're just unlucky and we just happen to exist in an observable universe where a void of this side exists. And it's really hard to say one way or the other because an odds of 1 in 100 is unlikely, but it's also not impossible or inconceivable for that to happen. So the nature of this cold spot is currently an unexplained piece of science.